Hi, I'm Russ Livesay. This is a review of some basic principles of charring. The purpose of this is to understand some of the fire forensic tools that can be used for identifying fire origins investigation. We're going to focus strictly on charring and loss of material. Today is April 29th, 2024. And I think one important principle that drives this is it's almost like a moral compass, points in a given direction. You have a real sense of mission for forensic investigation. An example is Cameron Todd Willingham, who was executed in 2004 for a crime that really never happened. Fire investigators concluded arson was involved in a 1991 fire, but modern forensics that utilize science and engineering principles have verified that there probably wasn't any arson involved with this fire. The question from that Texas case is how can we change things, focusing more on engineering and science to ensure false litigation, even criminal convictions like Mr. Willingham can't happen again. So charred material is likely to be found in nearly all structural fires, and this gives an impetus to focus on char as a forensic tool in analyzing problems. Um, Charring can have various rates. So what you can conclude is that charring for where empirical data is collected from laboratory tests, those char depths and the times to achieve those depths can be replicated in real fires if the conditions for the fire are firmly understood. Typically, at least the standard fire is defined as an ASTM E119 fire test. So that's a heating profile that materials are tested to. And if you apply that test, you can typically come with a range for char depth of 0.5 to 0.8 millimeters per minute. And there's ways to formulate and correlate the ASTM E119 fire test with real world type applications. One involves the very nature of a ASTM E119 test is that it's non-steady state. So there's some formulas you can use to correlate the ASTM E119 furnace test to more of a steady state application. So looking at the Q average here, this is a heat flux, and you can obtain an average for a given duration of the ASTM E119 furnace test, and then apply that into a formula to determine time that results in a certain char thickness. But the reality is you can conclude that char depth is going to be effectively proportional to actual accumulated energy transfer over time. And you can use that as a tool because depth of char may not be the most reliable metric to be able to calculate fire time. But what it can be used for is establishing an origin, identifying where an origin comes from. So relative depth of char is the key to show the direction of fire spread. Now you might, let's use an example. Let's say you have a relocatable power tap. It's an octopus plug with a portable electric heater plugged into it. And it's adjacent to some cardboard related ash, which is adjacent to what seems to be, a sofa that was ignited. You did a char profile that showed the greatest depth of char near that chair. You know that chair produced significant more overall heat or energy that was transferred into the wood than other locations. And looking in the vicinity of that chair, you can identify that relocatable power tap that was overloaded, resulting in your ignition source. That's the method that can be used with char to diagnose where a fire origin occurred. So when fire patterns are not visually obvious, you can use depth of char in terms of a survey, almost a map, to help identify where that origin occurred. Now this is a caliper. It's a standard caliper used for these kind of analyses, and there's a probe on the back end that allows you to set or to probe into the char. Char is kind of weak. You can actually penetrate it by applying a little bit of pressure with a probe pole. And here's an example of demonstrating just that from NFPA 921. Char depth is actually measured not from the cracks that develop. Char shrinks as it forms and it develops cracks and blisters. Look for the solid char in performing this depth analysis. Um, Comparison of char measurements should be done only for identical materials. So clearly you can have different materials such as, let's say there's oak, there's pine, say you even have some paneling. Um, Different materials are going to char at different rates. Moisture content is another factor that needs to be considered. So if you're going to do a depth of char analysis, it has to be the same kind of material. So some other factors that can affect char depth, you could be located next to a ventilation source. As stated previously, the ASTM E119 standard fire furnace, the actual products of combustion in that furnace are roughly 10%. So when you look at char rates for a normal 21%, which is equivalent to 23% by mass, 21% by volume, it's 23% by mass in atmospheric oxygen content. When you look at localized regions adjacent to ventilation sources that are producing higher concentrations of oxygen, that's going to char faster. You have potentially more depth of burn or material losses. Keep in mind too, the richer your mixture, the more products of combustion are going to have incomplete products of combustion, which is carbon monoxide. The char is, you're going to have thicker depths of char where you don't have oxygen. Thicker or more oxygen is going to have a cleaner burn. You may be more deeply penetrate into the wood, but at the same time, you may not have as much residual or leftover charcoal there because of a lack of oxygen, pyrolysis effect involved in that. So here's an example of a room. You can see the interesting blistering differences. Past forensic so-called experts have suggested that the differences in blistering may be accounted for by accelerants, and that's simply not the case. Here's a room from a fire test, homogeneous wall surfacing. It clearly shows differences that cannot be attributed to liquid accelerants. So blistering cannot be used as a tool or means of almost a binary pass-fail where accelerants used or not. You can't do that, but what you can do is you can take the char depth analysis previously discussed. So here's an example of a contour map from a room similar to this, where the gridded pattern of a 1 foot, 1 foot squares were used to take measurements from, and then those measurements plotted on a graph, a color coordinated graph. Shown here on the right is a map that shows the colors as a function of depth. And if you look at the black and the red location, which is adjacent to the door, that door being on the left, that seems to indicate the highest amount of energy was transferred in this location. So during further analysis, what an investigator should do is go and look and see, well, hey, what could have created the additional energy transferred here? Was this a ventilation effect because of the door exclusively? It may have been, but probably not in this case. You had another source of combustibles adjacent to it that ignited, burned vigorously, and allowed more vigorous charring at this particular location. In some events, you're obviously not going to have wood interior finish. You're usually going to have gypsum, sheetrock. But what you can realize is that sheetrock is going to have a specific heat transfer through it that's going to affect the interior wood studs behind that sheetrock wall. So here's an example where you do have a wall stud, drywall's on one side of it, but because of the heat transfer going into that gypsum, you're going to have some transfer to the wood stud, and if left long enough, you're going to have charring on that interior surface of the 2x4 or 2x6 stud. So here's an example that shows 2x4 studs, previously gypsum wall, clearly some depth there. And what you can realize is your studs, the deposition or the removal or creation, I should say, of char, it's going to be a function of, once again, your heat transfer into it. So the closer you are to the heat source, the more charcoal or charring you're going to have associated from that fire. The similar principle can be applied to floor fires. You can isolate just based on char deposition, or creation, I should say, on your floor joists under the subfloor where the fire could have been. And you trace back through basically depth of char to identify, well, where did the fire actually happen. Flammable gas leaks also can be used or diagnosed from this method. If you have a gas leak, let's say you have a natural gas leak with foam or some kind of a compartment, it ignites as a flash fire. Flash fires typically are not going to create char of any depth, but what you will have is greater char at the point of origin. So if you have a ruptured line of some sort, there's going to be residual gas that's going to continue being emitted from that pipe after the explosion. That's going to have localized charring whose depth is going to be significantly deeper when compared to the rest of the facility. So you can isolate where the leak occurred through this mechanism. Another location of charring differences is going to be at the door interfaces. A door that separates a cold and a hot area is obviously going to have leaks associated with the space under a door or around its threshold, as well as around the door frame itself. And you can use that to identify patterns. You have a lot more. There's variables. Let's be clear. There's variables in terms of how long the fire is going, pressure differentials, things like that. That's going to result in greater ventilation. But the real takeaway is if you have adequate heat, you have ventilation affecting that localized region of heat, you're going to have greater char depth. Use this to your advantage in diagnosing areas of potential where fire moved to or originated from. One other concept that needs to be considered regarding this principle is the effects of manual firefighting operations and overhaul operations. When a firefighter is going to go into a room post flashover, let's say, put out a fire, the whole process of having a fog or even a hose stream, it's going to knock off forensic evidence. It's going to damage charcoal. It's going to damage smoke patterns. So keep that in mind. Here's an example, an image that shows how active manual suppression activities from a fire hose have changed the profile of smoke patterns on this wall. So it's an important concept to keep in mind. Additional things to be considered on this. Here are different Class A or Type A and B fires. You have some liquid accelerants on the left side. Right side, you have Class A type materials, cardboard, plastic, polyurethane foam on different substrates. And what this demonstrates is there are some burn patterns associated with these topics, but it's easy to be deceived. For instance, here's an example of an actual burned building. No accelerants were used, but analysis of the floor could allow an untrained eye to conclude that accelerants were used. They were not used in this case. Here's an example of a laminate flooring where you had a cardboard box placed on top of it. You could conclude that there were some kind of a liquid pool or something along those lines that created this. That's simply not the case. So observation alone is insufficient to arrive at an appropriate conclusion. Here's an example of a carpeted floor where a test was done with some liquid accelerant, and it creates this donut-shaped charcoal where the middle is cooled via evaporation of that liquid, whereas the perimeter around this pool shows deeper char, and that suggests a liquid accelerant. But in all these previous cases, what it comes down to is additional laboratory test is necessary. You can't conclude from any of these images, perhaps this one is pretty obvious, but other images, it's really challenging to conclude that a liquid accelerant was used. Laboratory analysis through sampling will conclude that. So it's vital that those kind of samples are performed this kind of analysis. So keep in mind, char irregularities can come from several different effects. You have moisture content, ventilation, furnishings and fixtures. Furnishings and fixtures, a fixture could easily block radiant heat flux and consequently shield an area. And during overhaul that the fire department does when they go in and remove things, clean up, make sure there's no continuing smoldering fires, they're going to move those kind of things around. So it's very important that we recognize where things are at the time of fire. So be careful on conclusions. Char depth, it can be caused by increased ventilation. Identifying an area of origin simply because of the degree of damage has led to false conclusions. It's dangerous to go that way. The laws of radiative energy transfer are time, distance, and shielding. These are the fundamental rules that should be considered. They're valuable in our analysis. So the conclusion is char depth cannot be used to determine time of fire unless you fully understand the various conditions of that fire. if you can correlate it to an ASTM furnace fire, then there is value in performing an analysis, estimating time. But there's so many variables in there. It's a very dirty way of estimating fire. Charring has multiple variables that affect depth, so be very cautious when you're analyzing depth and correlating that with an origin. Make sure you look around to identify, was there a door, a vent, window that could have contributed to greater ventilation? What was the moisture content in that area? What was the type and species of wood there, for instance? All these factors need to be considered. Need to be documented that they were considered in terms of any kind of process. The reality is the best use of charging is for mapping the depth of char at various locations. What that does is it creates contours that point to an origin. That helps us identify general vicinity where the fire started. And then we can do further analysis in terms of, well, what was the actual ignition. So that's the process of using these tools. Charring can be a powerful tool if we're smart about it, but we have to do our forensic analysis appropriately. Here are some references that were used for this analysis. Thank you for your time.